so again, hopefully you printed this out. If not, you can just go ahead and do your work on a separate sheet. Homework 34 and lesson 34 are essentially the same. I'm going to do a couple of these with you and give you some hints, and then you're going to go ahead and work on the rest. So at the top, I know there's not a ton of white space, but there is a couple of hints I want you to write. So in this white space here, you should try to write down everything that I write down. I'm just going to go ahead and pop out to the side. Take a look at what it's saying. It's saying use each graph to find the requested information, use interval notation where possible, and reasonable estimates may have to be made. So not every graph is going to have perfect integer points, so you're going to have to give a reasonable estimate. And again, if you look at my answers and I said 2.5 and you said 2.75, because you're just estimating from the graph, that will be fine. So again, in this white space, you're going to go ahead and write the following hints and notes. I'm just going to do them off to the side. So first of all, let me remind you that when I am asking you for critical points, first, remember that critical points can also be called critical numbers or critical values. There are two main scenarios that make something a critical value. The first of which is anywhere that the first derivative is actually equal to 0. We've done that lots of times algebraically, but I want to make sure that it's clear that graphically, where the derivative is equal to 0 is anywhere that there is a horizontal tangent, which essentially means anywhere that there is a relative max or min. So graphically speaking, when you're looking for critical points, you're looking for places that have horizontal tangents or have any relative maxes or mins. Then remember, there's a second classification for critical values. Instead of saying where the first derivative is equal to 0, it's also where the first derivative is undefined. The three places that they're undefined, we've talked about them a lot, but now we have to make sure we can recognize them. The first place where the first derivative is undefined is at an asymptote. The second place is at a cusp. And the third place is at a vertical tangent. I'm going to show you one of each today to make sure that you know how to recognize them graphically. Again, we have done both of these classifications algebraically, but now we have to be able to do them graphing style. Any questions so far on that? You'll see it in the graphs in a second. The question was, what is a cusp? And again, I'm going to show you one of each today so that there's, so that you have a nice reference. And then the second thing that I want you to note here is that a cusp can never be a point of inflection. That is just the rules. A cusp can never be a point of inflection. You can, however, have a point of inflection on a vertical tangent. So again, those are just the rules. A cusp can never be a point of inflection, but you can have a point of inflection on a vertical tangent. So again, I'm going to show you visually what all of these things look like. That's actually kind of the point of this lesson and this homework. So if you feel like you're not 100% sure, again, that's the point of today. So take another couple seconds just to make sure you've got all that written down. There are 8 problems in total of all different kinds of shapes. I'm just going to do a bit of a random sample with you, and then you're going to have the rest of the period to work on the ones that remain. So if I go back to the worksheet here, notice that on the front side, all 4 of these problems are polynomials. Anything having to do with a polynomial, algebra or graphs, those tend to be the easiest ones. So everything on the front side is a polynomial, and that quiz on Tuesday is only going to be about polynomials for now. We're going to go ahead and do number 3. So even though it doesn't technically ask me for it, just as a reminder, this is an example of a polynomial whose end behavior is up, down. The only way your end behavior can be up, down is if you're odd and negative. Additionally, remember, you could say that with fancy notation. So on the left side, you could say as x goes to negative infinity, f of x goes to positive infinity. So as the x's get small, the y's get big. And then conversely, the right-hand behavior, as x goes to positive infinity, f of x goes to negative infinity. So again, I don't know how much you have to really worry about that notation, but it doesn't hurt to just mention it. Any questions on anything I've written so far? Okie dokie then. So when they say, where is the graph increasing, you should pretty easily be able to identify that region here. You would say that it's increasing from x equals -1 to x equals +1, and you would of course only use parentheses. That means it has to be decreasing everywhere else, which means negative infinity to -1, and then 1 to infinity. When they say find the coordinates of the critical points, remember, as I just went over, it's anywhere where the first derivative is either equal to 0 or undefined. When it comes to polynomials, which remember this whole front side is, you're only going to have to worry about where it's equal to 0. So you're looking for any place where there's a horizontal tangent line, which essentially means you're looking for the relative maxes and mins. So -1, 0, and then 1, 4. Questions? All right. In order to determine the concavity, again, you're going to have to give what would be considered a reasonable estimate. So as you start tracing the graph, it looks like you're holding the water. So concave up, concave up, concave up. To me, it looks like you're concave up all the way up to that point right there. If that is the point that you choose to believe that there's a change in concavity, then that would be your point of inflection. So I am estimating my point of inflection to be 0, 2. So the yellow part that I highlighted, I am saying this graph is concave up from -infinity to 0. And then it looks like the graph turns and becomes concave down. The water would be spilling out, and that would happen from 0 to infinity. So I don't know, maybe you could have done that without me, maybe not, but it certainly doesn't hurt to do a practice. You're going to do 1, 2, and 4 in a very similar fashion, and I would imagine that you would find it to be quite simple. You don't have to write in these things, but I do think that it might be helpful, so I'll leave that up to you. The ones on the back are a bit harder, so before I get to those, any questions on number 3? Okay, let's take a look then at number 5. So number 5 has no equations and has no numbers. So we're going to give our answers only in terms of letters, which is perfectly fine. The first thing I want to do is I want to highlight the fact that at E, that is what is considered to be a cusp. Why is it a cusp? Because it appears to meet at a point. So again, here at E, it looks like the two pieces are meeting at a point as opposed to meeting at a curve. So that is how you're going to identify cusps from this point forward graphically. It's where two pieces look like they're meeting at a point. So as I go from left to right, I'm going to try to identify any places where the graph is increasing. So I would say that's here, here, and then here. We're going to assume that the graph goes to infinity. So where is the graph increasing? First from A to C, then from E to F, and finally from H to infinity. The graph has to be decreasing everywhere else. So that would be from negative infinity to A, from C to E, and then from F to H. Any issues there? Okay, in terms of critical values, again, it's anywhere where the first derivative is equal to 0 or anywhere that it's undefined. So now we have to look for both. If you're talking about anywhere where the first derivative is 0, you're talking about the relative maxes and mins. That's here, 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 and here. If you're talking about where the first derivative is undefined, you're talking about the cusp, which is here. So all of those values are critical points. So we'll just say A, C, E, F, and H. No, so the place where the first derivative is equal to 0, those are the relative maxes and mins. Then you also have to consider where the first derivative is undefined, and that's where the cusp is. I'm sorry? Well, you have to consider both, right? Okay, so then we're going to go ahead and go back and take a look in terms of concavity. So concave up, remember, would be anywhere that you would hold the water. So to me, it looks like here is where the graph is concave up. And it looks like here is where the graph is also concave up. That would mean that here is a location where the graph is concave down. And here is a location where the graph is concave down. Any of the places where there's a change from blue to pink or pink to blue, those would be the points of inflection. So that would be B and G. And then you're going to go ahead and give the intervals. So where is the graph concave up? Those are all the blue spots. So that would be negative infinity to B. And then from G to infinity. And then where is the graph concave down? From B to E, and then from E to G. And just so you're wondering, yes, you do have to split that interval because of the cusp. You have to give something in your answer to indicate that there's something weird going on at E, which is why you have to break the interval. Questions up to here? Okay, obviously these ones on the back are a lot more complicated. All I want to do is just point out a couple of different things before I let you go ahead and try them. So in number 7, the only thing I want to point out is the fact that these pieces on the left and right are actually a little curvier than they look. So like it should look a little bit curvier as opposed to just looking like a straight line. So when you're determining concavity, again, they should be curvier. So if you want to write that in so you don't forget, feel free. In number 8, at -1, that would be a vertical asymptote. So as you go to identify places where the first derivative is undefined, remember that's one of the special cases at the vertical asymptote. There are other vertical asymptotes, but I just wanted to make sure I showed you one. So I showed you a vertical asymptote, I showed you a cusp, and now lastly, I want to show you a vertical tangent. So just so you're aware from this point forward, this is an example here at 0 of a vertical tangent. There are lots of different ways to think about vertical tangent lines. One way is that if the points look stacked, So see how they kind of look like they're stacked on top of each other at 0? That's one way to know that it's a vertical tangent line. Another way is the fact that it appears to be parallel to the y-axis, or parallel to the y-axis. In this case, it's on the y-axis, but if it was shifted to the left or the right, that's, again, another reason why it might be a vertical tangent line, if the line is parallel to the y-axis. And then the main reason is the following. At that location, the slope is undefined. Remember that a slope is a rise over a run. If you tried to find the slope of that line, the run would be 0, which would be undefined, which means you could not find the derivative. And again, the reason why this is important is because at that vertical tangent line, that's an example of a place where the first derivative is undefined. So at this moment, you should now have all the information that you need to complete the rest of the problems.